For centuries, empires defined their dominance with static stone monuments. Today, the pyramids of the modern age are mobile, cathedrals of steel and glass. These vessels are not merely floating palaces, they are sovereign feats of engineering that defy the fundamental laws of hydrodynamics. A single gigayacht represents an economic singularity. The construction budget often exceeds the entire gross domestic product of small nations like Nauru or Tuvalu. To keep 10,000 tons of marble, exotic wood, and high-tech weaponry afloat requires more than money. It requires a total rebellion against gravity. But what does it take to engineer a fully autonomous city that conquers the water? We plunge directly into the steel bones of the beast. If the modern shipyard builds floating fortresses, the Al-Mirkab is a cathedral of light. This 133-meter vessel challenges the definition of structural integrity. Architects replaced standard hull sections with reinforced structural glass. These are not windows, they are load-bearing components. The glass fights the ocean's torque, adding essential stiffness to the frame while flooding the interior with sun. Camera glides across cold, vein-matched marble floors. The reflection is blinding. Inside, the roar of the engines is reduced to a whisper. Yet below the waterline, the physics are aggressive. 9,000 tons of displacement. That is the entire weight of the Eiffel Tower, driving through the waves at 20 knots. The luxury of 10 VIP suites and a saltwater spa is merely the baseline. The true marvel is the Sky Lounge. It refuses to remain static. Automated bulkheads glide on silent tracks, physically expanding the room. Walls vanish. In minutes, a private dining area transforms into a massive hall for state receptions, a single architectural organism capable of reshaping itself on command. If the previous yacht is open to light, this one is built to be invisible and invulnerable. Meet the Eclipse. At 162 meters, it is longer than many active naval destroyers. The price tag breaks the €1 billion barrier, but this is not a holiday cruiser. It is a private warship wrapped in civilian paint. While guests relax in one of the two swimming pools, military-grade radars sweep the horizon for threats. The engineering focus here is pure paranoia. The hull is reinforced with armor plating. The master suite is encased in bulletproof glass. Even a camera lens is treated as a weapon. The anti-paparazzi shield is relentless. Infrared sensors scan the perimeter for the electronic signature of a CCD sensor. A digital camera is detected. In milliseconds, a laser beam fires directly into the lens. A flash of white light. The photo is overexposed and destroyed instantly. Luxury exists here, but it serves the security protocols. One pool features a floor that rises to become a dance floor, sealing the deck. Deep in the hull, a mini submarine waits in a wet dock. It can dive to 50 meters, allowing the owner to flee without ever surfacing. This level of readiness comes at a staggering price. Just to keep the systems running, the annual maintenance bill hits €50 million. On Motor Yacht A, security is not just about armor. It is dictated by the geometry of the hull itself. At 119 meters, the design abandons traditional flaring for a reverse bow configuration. A conventional ship wastes energy climbing over the crest of a wave, crashing down on the other side. This creates drag. It creates noise. Motor Yacht A does the opposite. The inverted bow targets the waterline like a combat knife. It does not ride the wave, it pierces it. This design acts less like a luxury liner and more like a surfacing submarine. By slicing through the water rather than crushing it, the vessel eliminates the violent vertical slamming of rough seas. Hydrodynamic resistance drops, fuel efficiency spikes, but the ultimate defense is independence. Advanced waste management systems process every gram of refuse on board, recycling fluids and compacting solids. The vessel can operate autonomously for weeks, leaving behind neither a wake of pollution nor a single trace of its existence. The aggressive exterior armor might fool the eye, but the true engineering challenge here is invisible. While the hull cuts through the waves, the interior fights a constant war against physics. The Al Said spans 155 meters and displaces 16,000 tons. That is the mass of a heavy cruiser. Yet inside the steel leviathan lies a professional concert hall designed for 50 orchestral musicians. This creates an engineering paradox. Ship engines generate low-frequency vibration that destroys acoustic clarity. A steel hull is essentially a giant bell that rings with every turn of the screw. The solution is total isolation. Engineers suspended the entire concert hall on an advanced elastic mounting system system, effectively floating the room inside the hull. This decouples the space from the ship's structure. On one side of the wall, turbines roar. On the other, a pin drop is audible. While the interior features gold and rare woods, the ultimate luxury here is not visual. It is absolute silence inside a working machine. To push this floating city through the water, the propulsion system ignores top-end speed records. The engines are tuned to deliver massive torque. Isolating sound is a complex calculation, but isolating a vessel from the temperature of a smelting pot is a task of a different magnitude. The Dubai, stretching 162 meters, serves as the floating fortress for Sheikh Mohammed bin Rashid Al Maktoum. Its primary operating zone is the Persian Gulf. Here, ambient temperatures routinely breach 45 degrees. The steel hull absorbs solar radiation until the metal becomes a thermal weapon. To maintain habitability, the vessel fights a constant energy war. The onboard cooling system generates the thermal output of a metropolitan shopping mall. It is a brute force solution to an environmental extreme. The result is a total separation of worlds. Outside, the humidity acts like a suffocating blanket. Inside, a central spiral staircase made of tempered glass remains cool to the touch, its steps illuminated by LEDs that shift color with the time of day. The engineering creates a microclimate completely divorced from the desert heat. But the structure must handle more than just temperature gradients. The upper decks are reinforced with heavy structural steel to accept vertical arrivals. A 9-ton helicopter slams its landing gear onto the hardened surface, transferring the dynamic impact directly into the ship's frame. From surface impact, we shift to internal physics. The heaviest object on board is not the steel structure, but the water captured inside. The Dilbar features a 25-meter swimming pool holding 180 cubic meters of water, 180 tons of mobile liquid. In open seas, this mass becomes a wrecking ball. This is the free surface effect. If the ship rolls and the water slams against the side, the momentum hits with the force of a falling train. To stop the vessel from capsizing, engineers built a hidden counter system. A network of compensation tanks surrounds the pool basin. Sensors detect a roll of even 1 degree. Within milliseconds, pneumatic valves fire. They inject a counterflow of water against the wave, killing the momentum before it strikes the wall. The violent slosh is neutralized into a harmless ripple. Stabilizing this giant requires staggering energy. The onboard power plant generates 30,000 kilowatts. This is not a standard marine engine. It is a power grid capable of lighting up a city of 40,000 people. While the interior is lined with rare woods, the true record is the density of the engineering. At 156 meters, Dilbar is the largest yacht by gross tonnage in history. Operating this machine requires a permanent crew of 96. Dilbar conquers with sheer mass, but Topaz, recently renamed A+, proves that a modern vessel's primary weapon is its nervous system. At 147 meters, this Lursen-built giant functions less like a yacht and more like a sentient machine. A dense fiber optic network integrates every system on board. This is a digital organism. From a single console on the bridge, engineers monitor the pressure of a specific valve in the engine room or the voltage of a light fixture on the upper deck. Total situational awareness. But intelligence is useless without stability. How do you keep a porcelain espresso cup motionless while facing a lateral ocean swell? The answer lies below the waterline. Topaz utilizes zero-speed stabilizers driven by rapid response hydraulic actuators. The process is a reaction war against physics. Sensors detect a roll microseconds before the hull moves. The hydraulics fire. The fins pivot against the current. The ship locks into place, defying the wave. Even the exterior paint serves the engineering. The white superstructure reflects solar radiation, passively cooling the hull to reduce the load on the air conditioning grid. Everything is calculated. With the stabilizers active, the giant sits perfectly still in the water, waiting. If Dilbar conquered through sheer volume, the next giant breaks the laws of physics with length and speed. Azzam stands as the longest private yacht in history, 180 meters from bow to stern, longer than a standard Arleigh Burke-class destroyer. Usually, a hull this long is a floating palace that barely moves. Azzam is different. It is a missile. To push 14,000 tons of steel to 30 knots, 56 kilometers per hour, traditional propellers are useless. The engineering team installed a hybrid monster in the belly of the ship. Two massive diesel engines work in concert with two aviation-grade gas turbines. The sound is deafening. The turbines scream, sucking in air and converting it into 94,000 horsepower. This energy travels down the shafts to 4 high-pressure water jets at the stern. Millions of gallons of seawater are sucked in and blasted out. The result is a rooster-tail wake that rivals a naval frigate on an intercept course. But speed creates vibration. The challenge was maintaining the open-plan architecture against the hull's torsion. The main salon measures 29 meters long by 18 meters wide, an open space large enough to park a commercial airliner, yet there are no support columns interrupting the view. To achieve this defiance of gravity while sprinting across the ocean, engineers concealed a web of high-strength steel beams deep within the ceiling cladding. However, Azzam's speed demands sacrifices in comfort, while Lionheart places its bet on absolute statics. At the Bonetti shipyard in Livorno, the design prioritizes material science over horsepower. The engineering challenge is maintaining stability for a structure that rises decks above the water. The solution lies in the density of elements. The hull is crafted from heavy steel, anchoring the vessel deep into the waves like a lead weight, 3,000 tons of displacement. In contrast, the superstructure is built from lightweight aluminum. This reduction in top weight lowers the center of gravity, ensuring the ship refuses to roll. This structural rigidity allows for complex mechanical articulation. High-pressure hydraulics drive the deployment of lateral terraces near the waterline. Steel arms extend, locking platforms into place with the precision of a bank vault door. Yet, the ultimate engineering feat remains invisible. Zero-speed stabilizers deploy underwater fins that counteract the kinetic energy of the swell. Sensors detect a wave. Fins adjust in milliseconds. While the ocean churns against the steel plating, the water in the upper deck infinity pool remains a perfect motionless mirror. Total isolation from the sea's motion. While Lionheart battles physics on the surface, the 134-meter Serene offers a radical alternative, escaping the motion entirely. Deep below the waterline, engineers carved out the Nemo room. This is not a simple window. It is a structural breach in the hull protected by glass thicker than a bank vault. Outside, the hydrostatic pressure presses against the pane with the force of a colliding truck. Inside, the air is still. You watch the abyss glide past in total silence. The isolation extends to the machinery itself. Aft of the engine room, hydraulic gates separate the ocean from the interior. Seawater floods a sealed chamber. A private submarine glides into the internal wet dock. The pumps engage and the water vanishes. But the ultimate engineering flex is thermal. On the upper deck, the tropical sun heats the aluminum to 40 degrees Celsius. Just a few meters away lies the snow room. Real ice crunches underfoot. The temperature plummets to minus 10 degrees. Maintaining a blizzard inside a steel box surrounded by humid marine air requires industrial-grade hermetic sealing. Total climate defiance. Every system on Serene is built to appear and vanish instantly. On the foredeck, a massive section of the floor retracts and the helicopter descends into a hidden hangar, leaving nothing but smooth, uninterrupted lines. From the hidden hangars of Serene, we return to the big picture of the industry. These floating sovereigns utilize more sensors and processing power than a mid-sized city. To reveal the sealed environments like the Nemo room or the internal dry docks, this investigation relied on neural network rendering and AI-driven structural simulations. We peeled back the hull to reveal the machine. Digital models expose what the human eye cannot see: complex hydrodynamics, stress loads, thermal isolation layers. Now the schematic is complete. The engineering is proven. The only remaining variable is preference. If the budget ceiling did not exist, which class of engineering would you secure for a global circumnavigation? The starting bid for this decision is $300 million.